Alright, silly people, here's the situation. We're in chapter 7 now, so we're doing Fourier transform stuff. Uh, the first problem is just doing the discrete Fourier transform on a set of waves. The first one being a square wave with amplitude 1. We got a sawtooth wave here and a modulated sine wave there. So he does say that we can start with the discrete Fourier transform.pi function that is on the online resources, so I did. Except I changed it a little bit so that it's not, uh, you know, I prefer to call the whole um, package whenever I'm importing stuff and just calling the specific functions that I'm using. So I changed that, but that's what that would look like, and we can get into doing the Fourier transforms of these guys. So let's also import numpy as np in here, and also import matplotlib.py plot as plt, so we can do the plots. And then the first function is again the square wave, so let's define a function called square, which is going to be a function of n, and capital N should out here say that capital N is 1000 evenly spaced points. And with the square wave, if the n over n happens to be less than or equal to 0.5, so just the first half of the domain of the square wave. If it's less than that or equal to that, then you return 1. Otherwise, return 0. And that's your square wave done. The sawtooth wave, he actually defines it there. You just have it return n. And then the modulated sine wave, modulated sine, again, he goes ahead and he defines it. So let's create a function of n and capital N to return, if I could type, the sine of pi times n over n times the sine of 20 times pi times n over n. Okay. If we wanted to, we could plot these. It doesn't really say that we have to, but I mean, they're all pretty explanatory of how they look. So I'm just going to get into calculating the Fourier transforms of these guys. So this function here, it doesn't take as argument a function because it's a discrete Fourier transform. It takes as argument an array. So we need to create an array for each of these guys. The only one of these functions that isn't array safe for inputs is the square wave one. So we will create a output list that starts off as empty, and then just run out for n in range capital N. Append that output list with square called at n comma capital N. The other ones are array safe, so we can just have y saw just be saw tooth called at the numpy a range, including 0 to capital N and steps of 1. Right. Same thing for y mod, which I'm going to use for the modulated saw or modulated sine. And again, you just call the function. For n, you run the a range from 0 to n in steps of 1, and then capital N for capital N. Right. So now that it has data to run through, we can create the Fourier transforms for these guys. And the reason it's called C is because those represent the amplitudes that correspond to given frequencies within the wave. So c square will be dft of y square. Seesaw, LMFAO, seesaw, will be dft of y saw. And then c mod will be dft of y mod. Pretty self-explanatory there. Let's create a plot of each of these guys now, just by doing a big subplot. So fig ax equals plt dot subplots. We only need 3, so let's do 3, 1 for that. And then the first plot, so ax index 0 will be or dot plt will be the square wave, so we just plot c square. And then for the second plot, we'll do the sawtooth, so we'll run c saw through that, ax2 plt, we'll do c mod, and we'll see what those look like in a second. Number of rows must be a positive integer. Sure. I'm bad at using subplots. And then axes objects has no attribute plt. Oh, we need to run plot, not plt. Yeah, again, I'm bad with subplots, but yeah. Okay. And also, you want to actually encapsulate the coefficients in absolute value functions because they're going to return complex values. So that way you can actually cast the behavior. But yeah, those are the Fourier transforms for the waves. I don't really know how to interpret those other than those are what they look like. So yeah, good stuff.